Hi there, thanks for joining us. This is a Q&A edition of Space Nuts. My name is Andrew Dunkley, same as it was last week, strangely. Coming up, we've got questions to answer. We mentioned recently that everything moves in the universe. Fred said that. It's prompted a question from JR. How do we measure that? Rod wants to know about the sun's fuel. Mick has a Mars hypothetical for us, and time permitting, we will be looking at wormholes and gravity. That's all coming up on this Q&A edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And to answer all those questions and much, much more, Professor Fred Watson. Hello, Fred.
Hello, Andrew. Hello.
I'm well. Long time no see.
So you're still called Andrew Dunkley?
Yes,
Yeah,
yes. Funny that.
I'm called Freud Prefect now.
Well, no one calls me Zaphod Beeblebrox, I'll tell you that much.
That's right. I didn't get enough offence for that.
No, that's right. If I was in Tasmania, however.
Don't go there.
Sorry. Oh, no. I crossed that line. I apologise. What do they say in Parliament? Withdrawn. That's what they say when they want to insult someone and then get out of trouble. Withdrawn. You're ugly. Withdrawn. Yeah. I love watching Parliament on TV. Do you ever do it?
Yes, because it's kind of almost part of my job from time to time to know about this sort of thing.
I don't know. I don't know what I get out of it because I just think democracy is so broken, and yet here I am, captivated by these grown human beings tearing strips off each other over ideology. Anyway, whatever. Shall we answer some questions, Fred?
Withdrawn.
We can do that too. We can do anything.
I'll answer some questions, yes.
All right, let's do that. Our first question today comes from JR. He said, "Hi, I've been listening to your show for many years, and for the first time ever, I thought I should ask a question." Yes, you should. What's the question, JR? I'm listening to episode 441, he says, and Fred said something like, everything in the universe moves, so I might as well too. Is that true that everything in the universe moves? How could we measure that? Thanks for everything, JR, who's in Ohio. Thanks, JR. Lovely to hear from you, and I'm looking forward to the Bengals season. They're looking pretty schmick for the football season in America this year. That's beside the point.
Not necessarily. They probably move too, I guess.
They move very, very well. Very, very well. I'm not sure about the quarterback's new haircut, but I can live with it if he plays well.
Yeah.
Everything moves, yes or no? And I think the answer is yes. And how do we measure that?
So we know everything moves just because the way in which everything's formed. If you think of the Big Bang, the sort of underlying scaffolding of structure we think was imposed on the universe very early on, which is this what we call the cosmic web, and we think it was dark matter. We think it was a web of dark matter, which itself is moving because the effects of gravity or the expansion are always to shove things along, and then more especially when objects that aren't made of dark matter, in other words, stars and galaxies, when they start forming, the formation process naturally imparts a spin to things. And so you've always got this interesting balance between motion and gravity. The two go together. It's almost a rule to say you can't have gravity without motion. Probably more accurate to say you can't survive gravity without motion because, and I'm talking now about things in space, it's the orbital motion of something around a gravitational object, a massive object, that stops it from being pulled in to the center. So we are always, if you've got objects in orbit, if you've got galaxies rotating, if you've got even the cosmic web has vibrations or has movements along it. It's all in motion. So you can measure a lot of it. JR's question is, how do you measure it? A lot of it we can measure directly. We can certainly measure the rotation of galaxies accurately. We can measure the motion of galaxies in clusters accurately. And on the very largest scales, we can measure what we call the proper motions of things. The peculiar motions of things. Their own peculiar motion relating to the Hubble flow, which is the flow of the expansion of the universe, which itself is in motion. So there you go. It's all moving.
It's all moving. It's like clockwork, isn't it, Fred?
Yes, very much so. That's right.
Yeah. Want to know who's winding it up, though?
It got wound up in the beginning. That's the bottom line.
Yeah.
So it's a very, very long-lasting spring.
Once the Big Bang happened, everything just happened afterwards by default.
Yeah.
So, and it's still happening. It's still going. It's still moving. We still see remnants of the Big Bang. Gravity's a big factor in the way things are interrelating. It's a cosmic dance, is what it is. All right. Thank you, JR. We got over that one quick. Yes, everything's moving. Yes. And we can measure that because we can. That's probably the answer. We've got an audio question, Fred. This one comes from Rod.
Hi, Andrew and Professor Watson. This is Rod from Bloomington, Illinois. Question for you about the fuel reserves in the sun. If the sun is consuming 600 million tons of hydrogen every second, why is it not dimming and shrinking? Does this mean that fuel is being replenished? Or are there some hydrogen atoms just waiting around to be burned in 5 billion years at the end of the life of the sun? Thanks. Long-time listener. Always enjoy the show.
Thanks, Rod. I really like this question because I find the sun to be quite a mystery because it's burning fuel at a rate that would, make a tractor unhappy. And you got to wonder about how it survives for such a long period of time if it's burning so ferociously.
Yeah, it's a process of, it's not so much burning, it's nuclear fusion. So
I was about to say it's probably more to do with nuclear activity than it is a pile of matches.
Yeah. But yeah, 600 million tons, it is a lot. But that's not just vanishing into the ether. What you get with the basic nuclear reaction that's taking place in the core of the sun, from that 600 million tons, you get about 596 million tons of helium. So there's something still there, and the deficit, the 4 million tons of hydrogen, basically are what's converted to energy. So it's that 4 million tons of hydrogen per second that makes the sun shine, that makes it so bright. Now that's all happening right down in the core of the sun. And the core is actually relatively small. It's the energy that comes from that keeps the rest of the sun, most of which is hydrogen, from collapsing. So you can think of the core as being the furnace and the rest of the sun being the fuel. Basically, it will continue to do that for, a few billion years yet, because the sun is so big and its reserves of hydrogen are so enormous. And so that's the basic process. I can't remember whether I said this, but the energy comes out mostly in the form of gamma rays and X-rays. There's other stuff as well, but that's the main thing. And you and I have talked before, Andrew. What's your name again? It's because I called myself Ford Prefect there. It's just sent me off on a different track altogether. Because, you can
call me Zaphod if you like.
Yeah, Zaphod. Well, last time we spoke about this, Zaphod, we went into the details of why we get light out at the end, and it's because of all that radiation that's generated in the core, basically. is absorbed and re-emitted by other atoms over a period of, what was it, 170,000 years or something like that.
Yeah.
It's getting on for 1 million years anyway, before it actually reaches the surface and comes out as sunlight. So interesting stuff. But I mean, the sun is stable at the moment. The balance between its gravity wanting to pull the hydrogen inwards and the radiation pressure coming outwards is perfectly balanced. But when that changes, once the sun starts burning helium, which will happen when it runs out of hydrogen, then basically the nature of the sun itself will change. And that's when it'll turn into a red giant star.
So it will, when it starts to deplete its resources and changes fuel, it will expand, and then when that burns out, it'll white dwarf.
That's right. Actually, this it's the envelope that expands. The nucleus will be collapsing slowly during that time until eventually it does become a white dwarf star. That's correct.
It'll get pretty cold here. Well, it won't. We'll be gone because we'll be absorbed, won't we?
Yes, I think it's going to be fairly ugly, I think, one way or another.
Well, hopefully we've paid up all our electricity so that we can charge the ion engines to get off the planet.
Yes.
Yeah. By then, who knows?
Going to need them.
Yeah, definitely going to need them. Thank you, Rod. Great question. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
I must confess, Fred, that when I prepared this show, I got everything locked in, all the questions written up, and now I've reached a point where I can't remember what this question is from Mick. All I've got written down is Mars Hypothetical. So, drum roll, please.
Yes, it's what happens if Mars gets removed.
Oh, that's right.
Hi guys, Mick here in Dublin, Ireland. Hypothetical question. It came about basically because I was thinking about rogue planets. So my understanding is rogue planets are planets that have lost their sun and more or less have been ejected from their solar system. I think this normally happens during the formation of the solar system. I'm not sure about that. But it led me to think, what would happen if something catastrophic happened to Mars? Like something out of a sci-fi movie where it was hit by a massive asteroid, or there was some massive explosion. I don't know. But let's just say ours suddenly left the solar system. What would be the effect on us and the planet Earth? Would we start falling in towards the sun because we don't have any gravitational pull from Mars? Or would we move out from the sun? Also, what would happen to the moon? I suspect something would happen to the moon because there must be some gravitational pull from Mars on our moon and on our planet. Anyway, just thinking out loud, not attending a voice message. Never done it before, so keep up the good work. Really love the podcast. Cheers, guys.
Thank you, Mick. Love the accent and great question. Thank you for sending it in. I was a rogue planet once years ago, Fred. I lost my son in a supermarket.
There you go.
It's a true story. It scared me willies. I found him around the corner in another aisle. But it's a terrible feeling when you lose your son.
When you lose your son, whether you're a planet or a parent, it's definitely a problem.
It's a great hypothetical. It's a great hypothetical, and my science fiction brain is suddenly sort of venturing towards Mars being obliterated by something, and Deimos has, making a beeline for Earth. That's the first thing I thought of. Yep, that's right.
That's your science fiction brain. So I think that the issue for me is that whatever gets rid of Mars is going to be the thing that makes a big effect on the orbit of Earth, rather than Mars not being there. I think if Mars had never been there, maybe the solar system would look similar to what it does now. There might be nuances of difference. We know that the planets have kind of wound up in a particular order, which is governed by something called Bode's law, and that has always been thought to be a coincidence rather than any real mathematical rule and regulation. But if you took Mars out of Bode's law, well, that means Jupiter might want to go where Mars is, or actually the asteroid belt would wind up where Mars was, in that sort of geometrical progression, and it would. So the absence of Mars would affect the Earth's orbit, because the Earth's orbit is modified slightly by what we call gravitational perturbations from other planets. Now, of course, Mars is not always on the far side of the Earth from the Sun. Sometimes it's on the other side of the Sun, so it's not always pulling us outwards. It's sometimes pulling us inwards. And all of that is taken account in the geometry of the Earth's orbit. I think the effect on the Moon, if Mars wasn't there, would be even smaller. There would be probably a tiny gravitational effect, again, perturbations, but the Moon is fairly tightly bound to the Earth in terms of its gravitational pull. It's only 380,000 kilometers away, so it's hung on to pretty well. So let's imagine a solar system without Mars. I think the Earth and the Moon would look much the same as they do already.
And still be livable as it is.
Yeah, probably, yeah. We might drift. We might, you kind of got to more imagine, rather than imagine Mars being dragged away by some mechanism which inevitably would affect the Earth's orbit. Whatever that was, it would be big enough to modify the Earth's orbit. If you imagine just Mars not being there, rather than Mars being dragged away, then it may change things slightly. It may change things enough that the Earth does get pushed out of the Goldilocks zone, but wouldn't be that much. But I think, that we're in such a sensitive balance of heat radiation from the sun and all the rest of it. It's a very fine line, perhaps, between humanity being here and humanity not.
Do we? You might have answered this in a previous episode some time ago, but do we know how wide the Goldilocks zone is?
Yes, you can calculate that, and it doesn't go as far as Mars, and it doesn't go as far as Venus. So I don't know what the width is, but you can calculate it. Yeah.
Yeah. Well, hopefully we're on the better side of it. We are at the moment, but
we're in the middle of it,
yeah.
which is the best place
so
to be.
In essence, if Mars didn't exist, things would probably be much the same as they are for Earth and the Moon. If Mars was destroyed by some evil force, let's call it, the Death Star, that might have a different impact on us because of whatever the force is that's caused this to happen.
Yep.
Maybe.
Quite so.
Suppose it depends on the level of catastrophe when you size it all up. When you look at other solar systems, their makeup is very different. In fact, ours is looking quite unique compared to a lot of the solar systems we're seeing, which have gas giants in close proximity to their parent star, and the rocky planets are further out.
Yeah. But bear in mind, they're the easiest ones to discover, the ones with gas giants closely in. So there might be a selection effect there.
Indeed. Okay, thank you, Mick. Lovely to hear from you. And if you ever have another question, please send it in. We've got one more question I think we can squeeze in. And this one comes from Diego in Slovakia. I have a hypothetical question for you. It's the second one today. If you would open a wormhole near an object with huge gravity, a black hole, for example, would its gravitational pull be transferred through the wormhole? Or would the bending of space-time just end at one end of the wormhole, and on the other side there would be only the local bending of space-time? Thanks for the answer. Love your show. That's from Gergo in Slovakia. I think we've heard audio question from Gergo before. But I like this one too. I love hypotheticals, Fred.
Yes, and So what the answer you're getting is also hypothetical.
Well, I guess it would be.
Yeah, I think the question will be: would the wormhole itself survive, having something, a huge gravity next to it? The gravitational field would modify the wormhole, and my guess is the wormhole would fill in, because wormholes are just such a special case of gravitational balances, if indeed they exist at all, and we've got absolutely no evidence that they do. So my guess is that the bending of space-time wouldn't just end at one end of the wormhole, which is what Gerko was asking. I think the effect of the gravitating body, supermassive black hole or whatever, would be to distort the wormhole and probably just turn it into another black hole, which would be immediately absorbed by the big one. It would be
existing
a merger. Yeah, that's right.
That in itself sounds like a very feasible probability if a wormhole ever turned up next to Sagittarius A star, for example.
Yes, yeah.
I suppose it depends on wormhole. I suppose it depends on how big the wormhole is, though, doesn't it?
Yeah, and I don't really know much about wormhole masses and geometry, but if you had a big wormhole, I mean, we'd know about something like that. We don't know of any candidate wormholes anywhere.
You know the best way to find a wormhole? Just look for the little piles of dirt on top of them.
That's right. They must be there. That's right.
Yes, that's. You can find a little pile of dirt in space, and you know there's a wormhole behind that. That's the way. It's a good question, but it's probably one that's in the realms of science fiction in terms of deciding what might happen. But yeah, I think when it comes to arm wrestles in space, black holes generally always win.
Yep, they're usually the winners. That's right, especially the big ones.
Yes, indeed. All right, go. Thanks for your question. Thanks to everyone who sent us questions, and you can send questions too via our website, spacenuts.io. Click on the AMA link at the top to send us text or audio questions, or on the right-hand side, there's another button where you can send us audio questions. Don't forget to tell us who you are and where you're from. We love to know, and who your favourite football team is. And thanks to Hugh in the studio, who is actually out picking up one of the kids from school, so he's done a great job. Thanks, Fred, as always. Nice to catch up. We'll do it again real soon.
I bet we will.
I think we will too. Yeah,
thanks, Andrew.
For sure. See you, Fred.
Good.
Professor Fred Watson, astronomer at large. And from me, Andrew Dunkley, thanks for joining us on this Q&A episode. We'll be back again real soon with another one. We'll see you then. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.